So welcome back, everybody. Today, we are going to mainly to focus on the solution of homework 6. I decided to make a video of the Fourier analysis. So I'm going to post that online. It's going to be a side topic, so you will not get exercises about it. But I think it's something which is useful for you to have seen, because you will encounter it in many, many other physics courses. But we will not use it here. So I'm going to make a small video of it, which I'm going to post either later today or tomorrow. The other thing which I wanted to say, and this is about a technicality which I just added. So you will obviously find you will find the videos online here for the different lectures. But in connection with the solutions of differentials equation with different numerical methods, I made a small video on this Runge-Kutta family of methods. So we are not going to spend too much time in the lectures, so you will find the derivations in the lecture notes, but you can also watch that video, and that gives you a background about different ways to solve differential equations. So just keep in mind that we have systems in mechanics which conserve energy, and then typically what you would apply would be a method like the Euler-Kromer or the velocity valet. If you have systems which are dissipative, you have a dissipation of energy, sorry for that. If you dissipate energy, then you have a non-energy conserving system. And then you're looking after methods which have a good precision numerically. That means that normally you have an error which goes like your step size in time, delta t, to a high power. And then this family of Runge-Kutta methods, although they do not conserve energy, so if you were to apply that to the solar system, if you run the solar system for millions of years, it would not conserve energy. But if you're thinking of harmonic oscillations, it does a pretty good job. And it has this method which is called Runge-Kutta to the fourth order, which you can see the derivations of in that video. There's a video on solving differential equations. That's a method which you have access now to via the lecture notes. You can use the codes as you want. Or if you prefer to use the ordinary differential integrator, which you have from CMSE 201, feel free to use that one if you're more familiar with that. So this is just a kind of a small hint and guidance about the material you can look up if you're interested. What I wanted to say something about is exercise 3. But before we do that, if we look at exercise 4 is actually me having you to look back at what we did during the lectures. And essentially you find the solution to exercise 4, the numerical one, in the lecture notes. So if you go back to, not this week, but the previous week, and you look up the slides and you go through that, you will find basically a guidance on how to solve exercise 4. So let's take a look at exercise 3, because there are some small things there which are useful and which become useful when we are looking at gravitational forces next week. So next week, we start discussing gravitational forces. So this force we are looking at, or this potential, which is called the Lennard-Jones potentials, is widely used if you do condensed matter physics and you want to simulate materials. So this is an effective force which people have parameterized so that you can fit the interaction between atoms and molecules in a material. Or people have been using this when they are designing new medicine. You run something which is called a molecular dynamics calculation, where you replace all of the microphysics with a set of coupled Newton-like equations, and where you have an effective potential. So this Lennard-Jones potential is one of these potentials which you will need in many different physics courses. But let's take a quick look at it and then see what is needed to do in the exercise. So let me just switch over to the text for the exercise. And for those of you which are online, after these few words here, we are going to go into the breakout rooms. So if you look at the exercise, what it says here, it has a potential which depends on the relative distance. Now, when you want to calculate the derivative of that potential in order to find the force, you have to think of a strategy for solving it. Now, if you remember back, the gravitational force, which we looked at the Earth-Sun for the Earth-Sun problem, that depended also on the relative distance. We did not take the derivative with respect to particle I or particle j, but we took the derivative with respect to the only variable which is in the expression here. So this expression depends only on a scalar, and this is called the relative distance. So you could go to spherical coordinates and take the derivative with respect to the angles and r, which will be your radius, which goes from 0 to infinity. Or if you want to really, how to say, make life difficult for you, you could take the derivative with respect to xi and xj. So that's going to complicate your life considerably. Now, the thing which we did some time ago was actually to take the gravitational force and take the derivative of the gravitational potential, and then we found the gravitational force. So let me remind you quickly of that, because it's basically the same thing. The only thing which changes here is instead of having r to the power of 1, we have r to the power of something else. Okay? So sometimes you can get a little bit overwhelmed when you look at this expression and say, how should I take the derivative? It's essentially the same thing as we did with the gravitational force, or you could think of the Coulomb potential between two particles. So this is a type of interaction which we encounter in many, many physics applications. So let's just quickly take a look at it and remind ourselves a little bit on how we can take the derivatives here. So I'm going to stop this sharing, and then we go back to the whiteboard. So if you look at the kind of potentials which we have now, so we have defined something which depends only on the relative distance. So this is now given by Ri minus Rj. And if we write it out here, this is going to be something which depends on xi minus xj squared. Plus, if we now are in 3 dimensions, this is y of I minus yj squared. And then it continues here. So this is zi minus the j component squared. So that's our expression here. Now, this means that we could now call this one for just a new coordinate x, and we could call this a new coordinate y, and we could just call this a new coordinate z. There's nothing which hinders us in defining this as the new degrees of freedom. And if you go back to the gravitational force which we had, if you think of that one, so some weeks ago, we actually looked at the gravitational potential. And the gravitational potential is also a function which depends only on the relative distance. And in that case, we had some constants, minus g, and then we would have something like a mass of the Earth, mass of the Sun, and this was divided by just the relative distance. Now we call such a potential, so this gives a scalar, just a number. You see also that it does not depend on any angle. So if you make a transformation to spherical coordinates, we call this potential for something as to be isotropic. So it means that it has the same expression irrespective of the rotation which we make. So if you're in 3 dimensions, you would have 2 angles and the radius r. And this potential depends only on the radius r. So when we want the force, in that case, what we did was simply to take, so let's rewrite this in terms of a parameter gamma divided by r here. So the Lennard-Jones potential, the only difference between this potential and the Lennard-Jones potential is that we have another power for r. So in this exercise 3, what we have is a potential which contains now something which goes like a new constant. Let's just call this minus v. divided by r to the 6 to the 12th, and a new constant, let's just call this for d0, divided by r to the power of 6. So instead of taking the derivative with respect to r to the power of 1 or minus 1, we need to take the derivative with respect to r to the power of minus 12. But let's see a little bit what we did back in some weeks ago when we looked at the gravitational force. So what we want now is the derivative of this quantity. And if we take the gravitational force, this quantity here, this is the same as minus gamma. And then I have my gradient of 1 over r, which again means that we simply have minus gamma. And then I have a d dx of I times this, so I have I here. This is the gradient plus d dy of j plus d z with respect to the z component k. And this is multiplied with 1 over r. So we're taking the derivative. And in this specific case, what we have is that 1 over r is just 1 divided by square root of x squared plus y squared and c squared, like this. So what we need to do then is to take the derivative of d dx. If we look at the x component, we need to take the derivative of this quantity here, of x squared plus y squared plus z squared. And if we do the derivative, what we are going to get then is something which looks like x divided by r cubed. And then we do the same with the y component of d dy of the same thing. And then we are going to get y divided by r cubed. And then we do the same thing with z, same expression. And then you get c divided by r cubed. And then if we go back a little bit, we see now that we need the different vector components, the unit vectors. So we would get then a force, which is equal to minus gamma. And then I'm going to get x divided by r cubed times I plus y times j divided by r cubed plus y times, no, z times k divided by r cubed. And we could bring that up, we could rewrite it in terms of the vector x and y and z. So we have the different components. And then we have a z times a k here. So that means that the force becomes equal to F of minus gamma times r divided by r cubed. Or we could rewrite it in terms of the unit vector of minus, and then we have 1 divided by r squared, and then multiplied with the unit vector r. Now, the complication you have is that you need to take d of dx of a function now which depends on this r to the power of 12, for instance, which means that you need to take the derivative of d dx of 1 divided by x squared plus y squared plus c squared. And then r has a power of 1/2. So this becomes 12 divided by 2. So that's to the power of 6. So the complication here is that you simply need now to take another derivative. That's the main complication compared with what you did with the gravitational force. So it's a little bit more labor, but it's not that difficult. So it's not the most exciting thing to do, but it's useful to have done it because you get an analytical expression for the force. And then the next step is actually to calculate the curl of this force. And you would proceed the same way. So the thing to think of when you look at a potential like the one you have in this exercise, where the potential depends on the relative distance only, is that you define a new coordinate. So instead of dealing with xi minus xj, you use the relative distance as the new coordinate. And you take the derivative with respect to the relative distance. Now, there's a reason why I wanted to bring this up, is that because next week, we are going to look at the gravitational two-body problem again, and we are going to derive the analytical expression for the Earth-Sun problem. We can actually do that for a two-body problem. But the trick, in order to do that, is to actually go through a change of variable, where we change from x for particle 1, x for particle 2, and so on, to the relative distance only, and the center of mass coordinates. So we're going to make a transformation of the variables to a new basis. And that's going to allow us to solve the equations analytically. So I just wanted to bring up this thing here, because I know that some of you were struggling with taking the derivatives of the potential. And then obviously what you need next to show that this is a conservative force is to calculate the curl of the force. So the final thing you would need to do is to, so there's quite some paper and pencil exercise here. So in the final one, when you have the force now, the next is to calculate the curl of the force. So you might say, this is not so nice of you to give us such an exercise on a Friday afternoon, because there's a lot of boring exercises. So I apologize for that. But I hope sometimes it's actually useful to have done these things, even though it's perhaps not the most exciting thing. This potential here is actually something which many of you may encounter in your further physics studies, especially if you do condensed matter physics, and if you're interested in simulating materials. Okay, so what we're going to do now is that Julie and I, we are going to float around as usual. George is going to be online. And for those of you online, we are going to use breakout rooms as usual. And for the rest of us here, we're just going to discuss in the classroom. And I'm going to stop the recording. And guys, feel free to raise your hands, ask questions. Never hesitate to ask questions, right? Okay. So for those of you online, we are now just going to move to the breakout sessions. And I'm going to stop the recording here. And George is going to run